Hello again, Calc AB, and this time our video covers powers of trig functions when the trig functions are secants and tangents. Of course, similar thing for cosecants and cotangents, but I'll just deal exclusively with secants and tangents today. So much like when we did sines and cosines, when we're talking about powers of secant and tangent, we're going to be using a similar sort of procedure where we think about the fact that they are related to one another through the derivative process, which links them together for then u substitution. Now, we know that the derivative with respect to x of tangent of x is secant squared x. So obviously, in order to make this substitution work, we're going to have to be u subbing tangent and looking for secant squareds in our integral. Or we know the derivative with respect to x of secant of x is secant of x tangent of x. So depending on the configuration of the integrand, we may be looking to sub out secant, which means we're going to look for a secant x tangent x term to combine with dx to be our du. In order to do this, typically what we do is we, again, look at the powers on the trig functions. So for example, if I'm looking at tangent to the sixth x secant to the fourth x dx here, which one of these does it seem likely we're going to use? Well, if you look at the derivative of tangent, we have secant squared, so we have an even power of secant. If you look at the derivative of secant, we have secant x tangent of x, both odd powers. So in the case of our integral right here, it looks like we probably want to use the one with even powers since we have even, and that's exactly what we're going to do. When we have secant to an even power, we're going to save a secant squared x, or theta, or whatever the variable is, to go with the dx and convert everything into tangent so we can do the u sub. So in this integral, it would look something like this. We'll take tangent to the sixth x secant squared x times secant squared x dx. And then we're just going to convert the secant squared, the remaining secant squared, or whatever power it is of secant, into tangent using our Pythagorean identity. Remember that we had sine squared theta plus cosine squared theta equals 1. Well, if you divide everything by cosine squared theta, cosine squared theta, cosine squared theta, you get tan squared theta plus 1 equals secant squared theta, which is precisely the identity we need to make this substitution work. So I'll come back to my integral here. I changed to blue, not sure why. It's all right. Tan to the sixth x. This will become tan squared x plus 1. And then we've got secant squared x dx out here. And now you can see we are nicely primed for a u substitution for tangent of x. So let's let u equal tan x du is secant squared x dx, which is exactly what we have ready to go. And we'll go ahead and make the substitution. So we have u to the sixth times u squared plus 1 du. This whole term becomes our du. At this point, it's probably easiest just to multiply it out inside the integrand. So u to the eighth plus u to the sixth du, which of course gives us 1/9 u to the ninth to 9. There we go. Let's make that look more like a 9. There we go. Plus 1/7 u to the seventh, and then we back substitute because we started with x. We're going to finish with x, and u is of course tangent 1/7 n to the seventh plus c. And there we go. So when we have our integral involving powers of secants and tangents that are in fact both even, save that secant squared, turn it into secant squared x dx becomes your du. What if we have odd powers? Well, then our other derivative pattern is going to be beneficial. If instead my integral had been tan to the fifth of theta secant cubed theta d theta, well, now I go, okay, I've got these odd powers. Those don't really work in the trig identities, but I do know that the derivative of secant theta would be secant theta tan theta. And so what I can do is save one of those factors of each one. So this will become tan to the fourth theta. This will become secant squared theta. And I save the remaining secant theta tan theta with my d theta. And now look, it's a very nice U sub pattern for secant. The only problem is I've got a tan to the fourth in here. Well, using the same Pythagorean identity we had before, right here, we can say, oh, well, tan squared theta is secant squared theta minus 1. So this is, oops, wrong pen. This is tan squared theta squared, secant squared theta, secant theta, tan theta, d theta. And that's where we'll do our substitution. So this is now 1 minus secant squared theta squared, secant squared theta, secant theta, oops, tan theta, d theta. And now you can see we've got just secants with the derivative of secant ready to go. So we'll have u equal secant theta. du is secant theta tan theta d theta. So let's make it happen. We get 1 minus u squared. Ooh, that's a u squared. U squared squared, u squared, du. Now we just go ahead and square that binomial out and distribute the u squared. So we're going to get integral of u squared minus 2 u to the fourth plus u to the sixth du. And go ahead and integrate that. Like so. And we start with x's, so, or I guess in this case we start with thetas, so let's finish with thetas. So we get 1/3 secant cubed theta minus 2/5 secant to the fifth theta plus 1/7 secant to the seventh theta plus c. And that's how we handle a power of trig functions when secants are odd. All right. Of course, these aren't the only ones that are going to show up in here. We're going to have some other powers of things show up. There's some interesting tricks that show up in secants and thetas. And there's one in particular that we're going to see happen a lot with integration by parts. And unfortunately, that's what we're going to have to do for this one. What happens in this integral of secant cubed x dx. Here's a pretty common one that we'll use integration by parts, and we're going to see a very normal thing happen with integration by parts. And I know we haven't seen it yet, so this is our first time with this. What's going to happen is I'm going to say, okay, this, as it sits, is a problem. I know if I split it like this, there should be an x in there. Okay. I have that secant squared, which I know that would be a nice du for a trig sub for tangent, but I don't have any tangents in here, and I only have secant to the first power. Okay. But because secant squared x dx is the derivative of tangent, it's also fairly easy to integrate, and it is much simpler as an integral, which sets us up nicely for an integration by parts. Okay? Because I'm going to let this be u and this be dv for our integration by parts pattern. Now, off to the side, of course, as I usually do, if u is equal to secant, then du is secant x tan x dx. So that's part of the integration by parts pattern. If secant squared x dx is our dv, then v is the integral of secant squared x dx, which means v is tangent of x. And that right there makes this particular integral doable with the integration by parts pattern. Because I know then the answer will be u times v, so secant x tangent x, minus the integral of v du. So that would be tangent of x times secant x tangent x dx. Now, with a little reworking of that integral there, we get secant x tan x minus integral of secant x times tangent squared of x dx. And as we said earlier in this video, we know what the Pythagorean identity for tan squared is. Secant of x tangent of x minus integral secant of x times secant squared x, there we go, minus 1, dx. And this is the interesting thing. If I distribute the secant, look what happens. Secant of x tangent of x minus the integral of secant cubed x dx plus the integral of secant of x dx. Think about distributing this secant here, and then also the negative one, and then we get two different integrals. Now, this is interesting because remember, what's on the left side over here of this equal sign? It's kind of gotten off the page, but remember, we started with the integral of secant cubed of x. So this has been over here the entire time. And notice what's in our integral on the right-hand side, the same integral. It's going to feel weird, but we're going to combine like terms. Not like your usual like terms, I know, but it is a like term that we can add to the other side. And so we have 2 integral of secant cubed x dx equal to secant x tangent x plus the integral of secant x. Well, we already know what the integral of secant x is. That's the natural log of secant x plus tangent of x. Now, we would, of course, have a constant over there once we took that derivative. And then all I have to do is divide by 2. And that's how we handle the odd power of secant of x. And it's clever. Secant x tangent x plus natural log secant x plus tangent x plus c. And that red c without the subscript is really just the old c divided by 2. And in integration by parts, this actually happens somewhat frequently, where in the process of doing integration by parts, the original integral shows up again, and just treat it like terms and add it to the other side, and that's all it takes. Okay, guys, in the section of the book here on page 534 and 535, they cover strategies for integrating powers of secant and tangent. There's a red box here on 534 for secant and tangent, just like there was a red box on 533 for sines and cosines. And as you work through, don't be surprised if the integration by parts technique yields some kind of original integral. Now, sometimes there's a coefficient in front of it, so you just combine like terms, and then you just be dividing by that coefficient at the end. All right, guys, that's it for this video. Hopefully this makes some sense. You're able to go back and watch it again if you need to, and we'll see you guys very soon.